Well, hello there everyone and welcome to part 2 of the To Be Astronomer reacts to the flat earth explanation for a downward vector, also known as Incoherent Electrostatic Acceleration. Let's continue where we left off.
Percent of their model to explain how it is possible. Having said this, I completely understand people's reluctancy to use gravity in any kind of discussion about the place we live.
Why though? We use it all the time. Literally half of the things that you witness every day probably are due to gravity, right? You look outside, rain falls, oh, that's due to gravity. You sit in your chair, that's also very much due to gravity. Don't know what he means there.
At the same time, most people who have never been educated on the subject correctly believe that
Most likely like yourself. Which is not to be an insult, but more like an educated guess.
force holding things in orbit and the force making things fall are one and the same.
Why? Could you elaborate on why those things cannot be the same or should not be the same?
In which lies the problem. It is hard to explain how this place works when most do not know how the laws of electricity control the world around us. I will try in this video to explain how incoherent electrostatic acceleration works while using examples that can be recreated by anyone.
Okay, curious about
To
that.
start out, we will take a look at Earth's electrostatic field. This
Cool.
is important because we, along with all the matter in this known realm, are inside of an electrostatic field.
Whilst that is technically true, because an electrostatic field is what's referred to in physics as an infinite field. It is infinitely distant, if you will. Imagine if there was nothing whatsoever in the entire universe, and you have a single electron somewhere in the universe. The electrostatic field, assuming that it has had enough time to disperse yet, to really get out there because it's moving at the speed of light. Imagine if you were, let's say, 3 megaparsecs away, right? Parsec is an astronomical unit, you can Google it. Imagine if you were 3 megaparsecs away, and if you had a measurement device that was sensitive enough and had no kind of interference and errors whatsoever, like a hypothetical perfect measurement device, you would still be able to measure the electrostatic field of that electron. So yes, everything is within an electrostatic field. With that said, a whole bunch of them are in such weak electrostatic fields that they might as well not be in any. So, think of if you are inside a Faraday cage, for example, the electric field in there is going to be like the smallest you can think of, negligibly small, tiny, for practical purposes, non-existent.
The Earth itself has a measurable negative charge compared to the air above it all across the plane. As soon as
I love how he says plane there.
you leave the surface, there is a positive charge in the air around you that grows in electrostatic potential.
That is true. There is that thing, although also how you can see, because you are connected to the ground, your electrostatic charge is always going to be, well, grounded, so for practical purposes 0, like 0 volts relative to the ground. And as you can see here, because this field, this electrostatic field, while technically I think it's 100 volts roughly every meter, while that is technically true, because you are also grounded and have 0 volts, it will move around you because you disturb it, right? But that's fine.
Compared to the air above it all across the plane. As soon as you leave the surface, there is a positive charge in the air around you that grows in electrostatic potential the further you go up towards the sky.
In principle, it stops eventually. There is a certain point at which it stops doing that, really, because the physics of the air in these extremely high regions become rather weird, and solar radiation takes a big part in that, because it is usually ionizing radiation, and things change up. But like until a very reasonable height, you can say that it increases.
Gradual rise in potential, which tells us, according to the laws of electricity, that we are between two Gaussian surfaces.
Oh boy, no, it does not. You would not be able to distinguish between an infinite Gaussian plane, right, or two infinite Gaussian planes, and a sufficiently large enough charged sphere, right? So I have to disagree with that.
A Gaussian surface is simply a surface that encloses or distributes a charge. If there were only one surface, the rate at which the positive potential grew would be different.
I mean, in classical electrodynamics, yes. The problem here is that he assumes here that Earth is a point charge, which it clearly isn't. It's a charged. I mean, for these purposes, I would describe it as a charged sphere. Really, yeah, that would be the better explanation for that. Yeah. I also like how he says that it couldn't be the same with either, but like he doesn't list any numbers. He doesn't list the like he doesn't give the formula for each. So I will have to do that later on. However, you can imagine if here, which is that's a very irritating figure. Here the equipotential lines are the blue lines, and here the equipotential lines are the red dashed lines. So that's a bit of an irritating thing, but whatever. And now imagine if you have a huge sphere, and if you zoom in well enough, these spheres of equipotential electrostatic charge, or like they would kind of look very flat. So that's more or less the same. They are not when we talk about strict formula, right? And I will have to show that at the end of the video in a small addendum, or maybe in a separate video. I don't know that yet. But like he says that, but he doesn't show it, which is great, you know.
Knowing that we are between two Gaussian surfaces.
Or in your case, just looking at it once and assuming.
We can also know that certain phenomenon will take place in all matter within the electric field, or area between the two surfaces. For this topic, we will first look at polarization through electrostatic induction.
Okay.
Electrostatic induction is a phenomenon where the positive and negative static charges on matter are slightly separated.
Yes, that happens. That happens, for example, if you have a dielectric medium. It actually says it here, dielectric. If you have a dielectric medium between two charges, the voltage between the two surfaces actually decreases, because really what you have is the voltage between this and that, and the voltage between this and that, and not the voltage between the two surfaces anymore. I remember that from electrodynamics, because that was one of the exam questions. But yeah, that's a thing that happens. For example, this happens in the dielectricon that's in between the conducting plates of a condensator. And it's not. Is it called a condensator in English? Hello again. Sorry for this small break. I had to Google what a condensator is in English, and it's a capacitor because I'm a potato. You know, sometimes I get those two confused, and I say capacitor in German and condensator in English, and sometimes I say one for each, because it's stupid that they have a different name, really, right? But, you know, whatever. It's called a capacitor because they hold capacity, of course.
Polarized due to the electrostatic charge of its surrounding area. If
yes,
one side of the object's surroundings is positive and the other negative, the negative charge on the object will be attracted to the positive area around it, while the positive charge on the object will be attracted to the negative area.
That happens. This picture is a bit optimistic, though, because it assumes that this happens to all of the charges in there. Usually there are some other kind of disturbing effects that make it like a statistical problem. But I assume that this is not a representative figure, but rather a figure to explain what goes on, and for that it's completely fine.
On the opposite side. So here on Earth, The positive charge on our bodies is always attracted down towards the Earth, and the negative will be attracted to the air above.
That is very
This
true.
phenomena
I
creates
mean, it would be true. But as you see in his own picture from earlier, right? This one, the field kind of bends around you because you disturb it. So I'm not sure if that's a good point. It's not.
force in that downward vector, because as soon as we leave the ground,
And that force just so happens to match what we predict for gravity. Wouldn't that force change if I was charged in any way? Shouldn't that force change during a thunderstorm, for example? Wouldn't that force change if I'm inside a Faraday cage? This thing would even change, now that I think about it, if I entered things that are like regions that are a bit kind of sectioned off with metal, for example. When I'm in a car, which for practical purposes is a Faraday cage, you're actually protected from lightning within a car. I assume you know that. How come that I'm not floating inside the car? I'm very keen to hear your explanation.
start becoming positively charged by the air around us and are now forced towards the negative of the ground. This is electrostatic acceleration.
Coming to think of it, I wouldn't float in the car according to his explanation so far. I would just be significantly lighter.
One might think that the attraction from above and below would cancel out completely, but it is the electrostatic gradient that creates a flow from the positive above to the negative below. Think of the Earth.
I'm not sure what he means by flow. He's certainly not talking about the electromagnetic technical term that is flow. Usually here, flow is referred to as a movement of charge, right? So charge times velocity, which nothing is moving here. It's called electrostatic acceleration, so something's off.
Flow from the positive above to the negative below. Think of the Earth as a flat strainer, and there is a constant flow of water from above, moving very slowly.
So why is it called electrostatic then? Also, no, there's nothing moving there. I mean, of course, there's wind and things like that, but I don't think that that's what he's meaning. He's saying that somehow the electrostatic field is flowing down.
Always applying
Or
a
something.
force in a downward direction. This would be considered a vector. The electrostatic potential difference getting stronger as you rise from the Earth will keep a steady pressure from above at all times until it reaches.
What if you're disconnected from Earth, right? What if you're hypothetically you're in an airplane and you jump out? Would you, if you move things through air, they become charged slowly but surely, right? If you jump out of an airplane, shouldn't you become positively charged and stay where you are at some point? The downward force would be completely negated at some point. You would most certainly, maybe you would continue to flow down, but you would most certainly slow down significantly.
The Gaussian surface above. When we reverse the polarity of the electric field and put a negative surface above a positive one, we can reverse this electrostatic phenomenon and get things to stick to the upper plate as if it were the ground.
That here is because clearly the electrostatic force, can become rather strong very quickly. You have already all seen a balloon like stuck to the ceiling or things like that because you charged it previously. It sometimes happens to me with plastic wrappers of food that get stuck to my hands and they won't fall down because the electrostatic force keeps them there.
This works with all types of matter.
I like again how there's no considerations put into this whatsoever, whether or not this could be any kind of other force, right? It's like he assumes inherently that there can only be one force acting on an object, which is crap. But okay.
Wood, iron filings, and even human hair with these forces.
Yeah, of course it can.
Believe it or not, you can even get water to bend.
Of course.
If the vector lines created...
You can do that with a comb and the water faucet if you comb yourself, and then you move the comb close to the stream of water that comes out of the water faucet, the water slightly bends. But that's neither here nor there. That's a very, very primary school experiment, but it's fun.
Between the two Gaussian surfaces
Yeah, and I'm at 15 minutes already again. Well, I thank you so much for watching, and I will see you in the next part. Until then, feel free to do all of the things that people do on YouTube, and I will see you in the next part. Thank you for watching. Bye! Hello everyone, and welcome to this small addendum to part 2, in which Good Times for All completely ignored the geometry, and he just said, well, things won't work with a ball, which I find funny. So here I have hyperphysics, and you have an electric field between two parallel plates, right? You have this here. He's done the same thing. He's just tipped it on the side, really. And so the electric field is this. Sigma divided by 2 times the electric field constant. Now, sigma here is the charge density, so charge per unit area. They explain it up here. Sheet charge density in coulombs per square meter. You can, yeah, that's fine. And you can see here that the electrical field actually, funnily enough, is the same pretty much everywhere. Can you see here how there's no dependence on radius anywhere? So it should be the same everywhere. Now, if we look at the spherical geometry, so a sphere of uniform charge, you see that for r bigger than big R, which is if we are outside of the radius of the sphere, this is our electric field. And you can clearly see, well, Q here is the charge, and then there is the electric field constant again. Then there's R squared. Aha! So the further up we move, the weaker it's going to get with R squared. That's a useful information. 4 pi is also there due to the spherical geometry part. Can you see how these two are not particularly alike? I hope you can. And I'm only mentioning that because he just says that, oh no, that doesn't work. He says it somewhere in the... No, he talks about it briefly here. There, he just says, yeah, here, he just says that you know, they are different without going into any of the specifics. That's usually how you know that someone doesn't know what they're talking about, is they avoid numbers and formulas. So I thought I'd just let you know, right? Great, so thank you for listening and things. You know, I already said it in the part before.